Good evening, everybody. Now, I just saw somebody I was supposed to be meeting. Miss Angela Nyirenda, how are you? Thank you for joining. Now, I don't know if you can hear me, but you're muted.
Yes, I'm okay, Doc. How
Yes,
are you?
I'm well. Just to apologize, the last couple of days I've been quite busy. There are a number of our students that have been busy making corrections, and so we schedule
Yes.
meetings, and then something comes up. Um,
Mm.
I want to suggest something. Check your
Yes.
calendar and tell me what time on Friday you think
Okay.
you'd be available to me, because Friday is cultural day at UNZA, so there are no classes.
Oh,
I normally
okay.
just have commitments in the morning between 10 and 12, but other
Okay.
than that, I can find time for us to have a chat. I think we really we are behind here. We need to have a chat. Apologies
E-
for that.
All right. Apologies accepted. I will check on my calendar and then I will email you.
Wonderful stuff. Thank you for
Yes.
joining, by the way. It turns out that this is usually a really wonderful opportunity to gain a sense of what happens research wise. I've always thought research is
Yes.
research, irrespective of whether it's engineering, social sciences.
Mm.
It turns out that I work with, in any given year, I work with students that are interested in the research that I do, but sometimes the research would be user centered, as is the case with people like yourself.
Yes.
Whereas in some instances, the students' interest would be more technical. So Elijah, for instance, is a classic example, and
Mm.
details of people that I work with on the website, of course. We're supposed to be adding your details as well. I've been so busy. We should be adding your details and a few other new people that I'm working with to the list here. But
Okay.
yes, in the interest of time, I'm not really sure if any other people are going to be joining us, but I was expecting to see a lot of people enrolled into CSC 5741, um, primarily because they're doing this for credit. Um, I don't think we need to be reminding people about that. So, but what I'll do is, just to be fair, I will just send um, a reminder to people uh, to say the talk has started, uh, so that hopefully they'll be able to join. A reminder that the talk, for the academic slash industry talk has started. Uh, okay, so without further ado, because we have a class, I think we may just have to start. But I'll ask our invited speaker, Elijah, if you are ready for us. I can introduce you if you are ready, and then we can start, I guess.
Yes, hello, Dr. Piri,
Yes.
and I'm ready.
Okay. Now I've seen a number of other people, right? Annette has been elusive here. Miss Mlenga, please, you must reach out to me. I was going to reach out to you like I did uh, Martin here, but it would be nice if you could send a hello message or something. We need to start our interactions. But anyway, we're not here to discuss that. That's fine. But I know she has heard me, I guess. I don't know. So today is, so thank you very much, everybody. I'm just going to quickly welcome or introduce our invited speaker. Um, but before that, just uh, maybe a quick note about why these things happen. So every year, we as part of the CSC 741 course, this is a data mining and warehousing course, um, uh, which is offered in the Department of Computer Science to students enrolled in the Master of Computer Science, Master of Science in Computer Science degree program. We have seminar presentations, and we tend to start these seminar presentations um, uh, quite quite late, I suppose. Our plan is always to start them after we cover certain important concepts. Okay, and I feel we've gotten to that stage now. So the idea is we normally have people from industry and academia come and give presentations. And deliberately, what we tend to do is, for most academic presentations, we tend to invite students that are either in their final stage of research, or sometimes people in academia that are doing academic research, people in industry that are doing academic-centric research, as is the case for Elijah. Okay, so today's talk is titled Large-Scale Analysis of Medical Image Metadata, and Elijah was gracious enough to send through a short snippet of what the talk is all about. But simply put, you notice that he's going to be talking about assessment of so-called DICOM files with a focus on DICOM compliance in medical images. I want to put it out there that I've been working with Elijah and a few other students for quite some time now, a year plus, I want to say. I started working with Elijah a while back, actually, when I was still an undergraduate student, but he happens to be one of the students that we've been working with as part of the Enterprise Medical Imaging in Zambia project. I'm going to share a link to the project website, and also a direct link to a list of core people that are working on the project itself. The project has gracious funding from 3 entities. So we have funding from the University of Zambia through the Directorate of Research and Graduate Studies. We also have funding from Google Research through their award for their Google Award for Inclusion Research program. And then we also got funding mid last year from an entity called Data Science Africa. All of these entities, so Data Science Africa, Africa, would be of interest to people enrolled in CSC 5741 because what they do, and I guess we are late here, but what they do every year is they have what they call summer schools. Summer schools that are typically aimed at postgraduate students. So in some instances, they'll provide you with travel funding so that you go and attend these summer schools. This year, for instance, the summer school is going to be held in Nyeri in Kenya. And I'm happy to say that one of the students I'm working with was actually given, Malaya UTHs, was actually given a travel grant. So he'll be traveling there to go and present his work and engage with other researchers that are working in and around areas of data mining, machine learning, and artificial intelligence. So I thought I would mention that, right? So Elijah is a research student at the University of Zambia, focusing on enterprise medical imaging in Zambia project. He also works as a full stack developer at Qualikeep Investments Limited. Previously, Elijah served as a tutor at the University of Zambia, where he taught courses in software engineering, project management, computational mathematics, and databases and web technologies, and mobile application development. He completed his postgraduate diploma in computer science from the University of Zambia in 2023. That was last year. Elijah is going to be graduating in this month, actually. And following his bachelor's degree in information communication technology education, which he obtained in 2022. So Elijah, the floor is yours. I am going to unshare my screen and then hand over to you. And just to mention that a heads up, I don't think we have time here to get informed consent from people, but we record these sessions and we archive them publicly. So the Q&A session, but also the presentation itself. Part of the reason we do that, by the way, is because this activity counts towards credit for the people enrolled in CSC 741. The recordings helps us identify individuals that would have attended and also actively participated. Thank you very much. Elijah, you can share your screen, and over to you. And please let us know if you would want people to interrupt you as you are presenting if they have questions, or if you'd prefer for them to wait until the end until the end for them to ask questions. Thank you. Over to you.
All right. Thank you very much, Dr. Piri. Let me just share my screen. Oh, am I audible enough?
Yes, you are loud and clear, at least from my end.
All right.
And yes, we can see your screen now.
All right. All right. All right. Okay. So my name is Elijah Chileshe. And before we start, I would actually like to say thank you so much to Dr. Piri for inviting me and enabling me at least give a talk just to explain some of the things that we have been doing as part of the Enterprise Medical Imaging Project in Zambia. All right, so the title of my presentation is Large-Scale Analysis of Medical Image DICOM Metadata. And the outline of this presentation is as follows. So we'll simply have an overview of what this particular work package was about, which is large-scale analysis of medical image metadata. And we'll look at the importance of medical imaging. We'll look at the methodology, and the last part being the conclusion. All right, so Zambia, like most countries worldwide, is faced with a shortage of radiologists. And as of 2019, it was stated that there were only 5 trained radiologists working to save a population of 17 million. And the EMI project looks into this particular challenge of the shortage of radiologists and tries to explore potential enterprise medical imaging techniques that can be implemented to help streamline some of the medical imaging workflows that are currently available. So by investigating the feasibility of implementing efficient systems, this project aims to showcase how enterprise imaging could be used to alleviate some of the significant challenges that are currently being faced in the medical imaging sector in Zambia. All right, so I would like to mention that the enterprise medical imaging project actually has about 7 work packages, but our main focus is going to be on medical image analysis, which is work package 3. And if you look at the link below on the bottom right, this link will then redirect you to the official EMI project website page. All right, so the image that you are seeing right now simply displays the current radiological workflow that's followed at the university teaching hospitals. And in order for a patient to have an examination performed, what needs to happen first is that an order first needs to be placed by the referring physician. And once the order has been placed, the order will then be given to the radiographer, sometimes known as the operator. So once this operator receives the order, they will then generate the medical image. So by carrying out an examination on the patient. So once the examination has been successfully carried out, a medical image will then be generated. And once that image has been processed, it will then be interpreted by the radiologist. And once the radiologist interprets that medical image, a report will then be generated. And for work package 3, which is large-scale analysis of the medical image metadata, our main focus is going to be on the medical images that have been generated after an examination has been performed. All right, so this work package focuses on the exploration of a systematic analysis of medical image metadata using the DICOM standard. And as mentioned earlier, this work package is part of a larger project, which is the EMI project. And some of the data that we used during our analysis came in from the university teaching hospitals as well as Levi Mwanawasa Hospital. We had a total of about 4.5 million medical images that were generated within the past 5 years. And the same 4.5 million images is one that we actually used as our data set. And the main focus was for us to assess the DICOM compliance levels. Right, so what is the role of medical imaging in healthcare? So some of the roles of medical imaging in healthcare include enabling accurate diagnosis, as well as providing visual insights into some of the internal structures within the body. So for example, let's say if a person has got a broken hand, once a medical imaging examination has been carried out, it will be easy for the radiologist to look at those parts of the image, or rather those parts of the body that can be seen by naked eye. So for example, if you look at the bones, this medical imaging is going to help us have a look at some of those problematic areas. All right, so regarding the methodology, we used the CRIS-DM methodology, and I'm sure most of you are aware about this CRIS-DM methodology. So CRIS-DM simply stands for Cross-Industry Standard Process for Data Mining, and to put it in simple terms, it's simply a step-by-step guide that helps people that are working on a data mining project. The CRIS-DM methodology has got 6 phases. So one of the phases, or rather the first one, is business understanding. So within business understanding, this is where you get to understand the business needs. And this is where you also identify how do these, or maybe how do some of these challenges affect the business. Then we also have data understanding on the second phase. So in data understanding, this is where you get to know what kind of data you're working with. All right, so what data are you working with and where is it coming from? The third phase, which is data preparation, this is where we now get to clean the data and organize it so that it's ready for feeding into the models that are created. The fourth stage is the modeling stage. This is where we now get to create the different models. The fifth stage is the evaluation stage. This is where you now get to assess or evaluate the models that have been generated. And once you assess the models that have been generated, you can then specify whether they do fit the business needs. And the last stage being the deployment stage. This is where you now get to incorporate those models into the business itself, as well as view the results that have been generated. All right, so when creating these slides, what I did was that I had tailored them to include both the methodology that we used, as well as the different stages that we used during our analysis. So if we look at the business understanding, now in relation to our work package, the objectives include assessing the compliance levels of the DICOM standard through carrying out an analysis on the metadata. Then we also, or rather another objective is for us to automatically classify the medical images. Our focus is on carrying out an analysis on the metadata within the DICOM images. And I'm sure you've been hearing me mention the term DICOM. So what does DICOM stand for? DICOM stands for Digital Imaging and Communications in Medicine. And this is a universal standard or format that is used for storing medical images, as well as exchanging these medical images between different devices. All right, so what is, or rather what makes the DICOM standard unique? If we look at the different file formats, we also have PNG, we've got JPG, but in medical imaging, most of the time, the DICOM standard is used. And the reason why the DICOM standard is used is because it helps the medical personnel to store important patient information within the image itself. So you might find that a medical image would have details to do with the patient's name, patient ID, the operator's name, who was carrying out that examination, who referred that patient, looking at details as well to do with the institution, what department as well. Right, so this image that you're seeing right now is an image of an X-ray machine. This is an image of a CT scan. We've got an MRI, as well as an ultrasound machine. So these 4 machines that I've showed you here all generate DICOM files. All right, so if we go to the next phase, which is data understanding, this is where I mentioned that we need to understand the type of data that we are actually working with. All right, so in our case, we're working with DICOM files, which have got an extension .dcm, and our main focus was on extracting the metadata that was found within the DICOM files in order for us to carry out the analysis. The table that's currently being displayed shows some sample DICOM metadata elements that are found within the DICOM files. So the first column that we have here shows the attribute names. So the DICOM files contain details to do with the modality. Was it a CT scan? Was it an X-ray? Then if you look at the study description, this simply displays or describes what kind of study was performed. Then we also have the patient name. We've got the patient ID and the series instance, UID. Then we also have the tag column. So the tag column is one that we're actually using when pulling this information from the DICOM file or when extracting this information. The sample image that you are looking at right now shows an example of a DICOM file. So we used an application called WeAssist to open this medical image, and as you can see, this is a chest X-ray. So we can see some of this information that is being displayed. We can see the patient information. We can see the station details, the study details, the series details as well. All right, so during the data preparation stage, this is where I now get to clean the data and organize it so that it's in a form that can be used to feed into the models that have been created. And so what we had to do was extract, or rather remove the corrupted data and standardize the data so that it's in one format or a standardized format. And then we also had to choose specific DICOM elements that we were supposed to use for the analysis. I would like to mention as well that the DICOM standard itself has got 5,000 plus DICOM metadata elements. But our analysis was on the fields that are entered by the operator when an examination is being carried out. All right, so this image simply displays some sample information. So as you can see, in 2020 July, we had about 3.2 gigabytes worth of information. In 2021, we had about 180 MB and 6.5 GB. But this is just some sample data, but what the information that we used, or the data set that we had about 4.5 terabytes worth of information. And so still during the data preparation stage, we also had to go through the process of digitalizing some medical images. So once medical images have been generated by the operator, these images are then stored on CDs. So once these images have been stored on CDs, what we had to do was simply obtain these CDs and then copy all the DICOM files that were stored on these CDs, put them on an external hard drive to make it easier for us to have access to the medical images. Then if we move on to the modeling stage, this is where we now get to implement the algorithms that were supposed to be used to carry out an analysis on the DICOM metadata. And some of the techniques that we used included exploratory data analysis. So we just wanted to gain a firm understanding on the type of data that we're working with. And some of the tools that we used when coming up with these algorithms include Python, as well as Jupyter notebooks. In the evaluation phase, this is where we now go to measure the compliance levels based on the selected DICOM, the DICOM elements that we had selected. And we also had to verify the analysis and accuracy. We had to verify the analysis on the accuracy and reliability of the model that we had implemented. And the last stage being the deployment stage. This is where we now go to visualize our findings and see whether the model was working as it was supposed to work. And based on the information that we found, this information is able to actually help us come up with guidelines that are supposed to be used when specifying important information that should be entered by the radiographers when generating the medical images. Right, so the image that you're seeing right now shows the results that was generated after carrying out the analysis. So the bars that you're seeing in blue show that those fields were not missing, while the ones in red show that those values were missing from the data set that we had. So in the y-axis, you can see the different DICOM metadata fields. So which is the study date, we've got the modality, we've got the patient sex, we've got the patient's age, and the rest. So from this, from these results, we can actually see that the compliance levels regarding the DICOM standard at the university teaching hospitals are quite low. All right, and so in conclusion, this study simply focused on conducting a systematic analysis of the DICOM metadata. So while looking at the level of DICOM compliance, so by carrying out an analysis, we're able to now identify whether the radiology department focuses or are they compliant with the DICOM standard. And based on this information, we're able to now generate the necessary documentation needed in order for the compliance levels to be at least increased compared to what we currently have. All right, thank you. This is the end of my presentation.
All right. Thank you very much, Elijah. Thank you very much. As I've always thought, so no, I don't invite questions, but I think I must say this. You know, when we started working on this project back in 2021, I was together with an old friend of mine, somebody I met when I was in high school. We were together at UNZA, but he decided to pursue a degree in, well, he's a medical doctor anyway, but he specialized in radiology, right? So it started off through conversations, and at the very beginning, I was quite blank in terms of what happens when you're dealing with radiological workflows, right? The only thing I knew was that when I was sick and an image needed to be generated, so I've been in instances where you go and see a doctor and they say, well, we need an x-ray done or something, right? I remember, I've had this long-standing backache. So one time I got Coptic and tell me, you need to go downstairs or you need to go to this room to go and get examined. You know, an x-ray is generated and then the operator will tell you, go to room, maybe room 5 or something and submit this x-ray. You go to that room and you're told to wait. There's usually a queue. It's quite sad, actually. And it's the same. I've been to Maina Soko. It's worse at UTH, right? There are queues. It turns out that when you're queuing up outside, you're waiting for an expert radiologist to actually interpret the image. And once they do that, they'll print out a report, say, go and give it to the referring physician. It took a while for me to appreciate this. And I do hope that none of this went over your head, as Elijah was talking about this. But just to mention that the way the metadata, the DICOM metadata is stored in the file is similar to what typically happens with a photo. I'm working with students, and not too long ago we were actually looking at image metadata, right? You know how you can actually generate. Well, when a photo is generated, you can use tools like EXIF2 to generate a dump of metadata, things like GPS coordinates, the type of device that was used, the model, and all those things. Of course, I mean, if you send it via WhatsApp, all that information is going to be stripped out because of security concerns. But simply put, what we were doing, in case this went over your head, is there's a problem with metadata. The metadata, the crucial metadata, most of the crucial metadata is entered by operators. Sometimes metadata misses. Like you won't find the gender of the patient, the age will be missing, or the date of birth really, because the age is derived. So our analysis was aimed at trying to assess the compliance levels. I think in the interest of time, maybe Elijah had missed out an important part. There's another detailed analysis that was done, the actual compliance, because what he showcased was just, I guess, just distribution of now and non-now values. But we've gone beyond that. And we've quantified compliance in a certain way. But anyways, I will invite questions. I thought I would mention that. I will invite questions. I don't know if people have questions. Please go ahead and ask away. You can raise your hand, and then seeing as there's quite a number of people, we can then take turns and have Elijah address your concerns or questions. It could be general, maybe something to do with radiology. Yes, Lloyd Hangoma.
Yes, sir. I never got the part where they evaluated the same DICOM system or something.
Yeah, Elijah is asking about how you evaluated the DICOM system.
Sorry, I'm not sure where I got your question. What do you mean evaluated the DICOM system?
Okay, so from what I got, we from the stages that you like went through, I never got the part where you evaluated the same thing. So I'm not sure if it was done or it was not necessary in this case.
It was actually done. So what we did was during the analysis of the medical images, what we had to do was create a data frame. Then after we extracted the relevant information from the medical images, we stored them within the data frame and then started carrying out the analysis from there. So what we also had to do was check for the null versus the non-null values.
So I think the questions, I kind of get a sense where these questions are coming from. I don't know if you had prepared the data frame, if you have it, because we can only see your Google Meet thing here. But if you could showcase some of these things, maybe it will make a lot more sense. But also, I think part of what, I mean, not that I'm speaking on your behalf, Mr. Hangoma, but part of what Lloyd is trying to find out, by the way, is when we're discussing the CRIS-DM, we finalized discussing it on Sunday, by the way, at the makeup class, right, in 5741. We made mention of the fact that during evaluation, what you do is you evaluate the model against the business objectives. And so his expectation is if there was a classifier, for instance, what was the relative accuracy? I think this is what he's hinting at. Is that the case, Lloyd?
Yes, sir.
Yeah.
I wanted to ask even the success, is it the success rate of the same thing, if it was 80% or 90% or yeah.
All right. So we didn't actually implement an AI model or a machine learning model, but what we did was that we had assigned some weightings to the different metadata elements. All right. So what we did was that we assigned the weighting score of 1 to the mandatory fields. So those fields that are inserted by the operator while they are trying to carry out an examination. Was during the generation of the medical image, when a patient sees the operator then starts entering the patient information within the machine itself. So once that information is stored within the machine, that information is then stored within the DICOM file. So what we did was that for that information that is entered by the operators, we assigned a weighting score of 1. And then for the information that's not really necessary, we assigned a weighting score of 0.5. And then for those that were completely unnecessary, we assigned a weighting score of 0.
You know, Elijah, by the way, maybe people will be able to remember more about some of these questions if you would at least navigate to a slide that has, there's a slide that has a DICOM viewer. Currently, we can just see your Google Meet screen. That may preempt questions, if you will, I suppose. By the way, this slide again is typically what the radiologists would see, right? It's an example of a tool. It's called a DICOM viewer. The situation is quite sad, right? At UTH, for instance, I mean, the numbers are slowly increasing because it turns out that government has actually instituted a number of other initiatives. Like, for instance, they are training radiologists. But the thing is, this is specialized training. It's not like a master's in computer science that you do within a year or two, right? These people will only graduate after 5 years. So my colleague Ernest was only graduating, or is only going to be graduating this year in June, after 5 long years. So it's quite sad, really. But any more questions? Oh, yes, please. There's a question from Chela. Please go ahead. Thank you.
Thank you. I had a few challenges with network, so maybe I might have missed 1 or 2 points. Was the project more centered on trying to see if UTH follows, is it the DICOM standard, or it was centered on once you review the image, you also try to find maybe the disease the person might be having. Perhaps I missed a point or two. You can clarify on that.
All right. Okay, so it wasn't focused on trying to identify the diseases that the patients had, but our focus was mainly on the metadata, so the information that is entered by the operators. So there's some mandatory values that are supposed to be entered by the operators, but most of the times you might find that even from the results that we have here, you can see that the bars in red indicate that these values are missing. They are now, so for the entire data set that we had. So our main focus was on carrying out an analysis to see whether these people, so the radiographers, do enter the necessary information. I'm not sure if I answered your question.
Yes, you have answered my question. Maybe a follow-up question on that. So far with what you've done, is it possible to cover that other area which I mentioned? I say so because I think for an individual, maybe Dr. Lighton had given how long it takes for one to have their full analysis of whatever had happened there. I don't know, maybe you can shed more light on the challenges which might be associated with what I'm currently trying to put forth, sir. Thank you. I hope you've gotten my question, sir, or what I'm trying to say.
Okay, I'm not really sure I really understand, but maybe Dr. P, you can help
Well,
out.
I mean, I can attempt to, and then as I'm doing this, maybe want to also showcase. You see, people only see value in what you are doing if it's so obscure. If you have a specific use case scenario, right? We have access to the Xamarin instance. Maybe you can fire up the PAX platform that we've deployed on Xamarin servers, and speak to that later on. But to answer your question, right, Chela, you see the thing about what we are, the thing about what we're doing is it's multi-pronged. What Elijah has spoken about is one of 7 work packages we're doing. I'm tempted to invite somebody to come and, Malaysia, to come and give a talk centered around what you just raised here next week, maybe, or after next week. Work package number 6 is it was aimed at building AI models that would help with semi-interpretation of medical images. Now you see, if you sit with a radiographer and you ask them how long it takes to interpret a medical image, depending on the pathology or the modality, whether it's an MRI, CT, or an X-ray, it takes time, right? In fact, there are certain modalities that will have thousands, if not millions, of slices, like when it comes to brain imaging or something. And so what work package number 6 does nothing to do with what Elijah was saying here, was presenting, but we've built a detection and a classification model that is focused on one pathology, pneumonia, right? It turns out, right, when these people are looking at scans, for instance, if you have an infection in your chest, it could be tuberculosis, it could be pneumonia, it could be cancer. But what we've done is to demonstrate some of the things we're doing, and then within the limited scope of the project itself, because the project has a timeline, is we just built models for one pathology. So that's what we've done. Something else we've done in terms of AI is, as part of work package number 7, there's a colleague of ours colleagues from UCT, the University of Cape Town in South Africa, building solutions that are meant to help with generation of reports. You know, when a radiologist gets a hold of the image and they do the interpretation, the next task, I don't know if Elijah can go to that nice workflow here. The next task is they have to produce a report that will say, oh, Lighton has pneumonia or something, right? That's the transcribed report stage. That process takes time because the radiologist has to sit down and they have to type. So the idea behind work package number 7 is, can we automate, not completely, but can we automate the process of generating the report so that instead of it taking the radiologist 30 minutes or maybe 45 minutes to prepare that report, and it does take a while, maybe it will take them half the time or something. So in terms of AI, those are some of the things we've done. But relative to what Elijah has been doing, if Elijah can go back to the PACS platform, you see, when these people are looking for this, a lot of images are generated, right? People who go to UTH or Maina Soko for specialist treatment, I mean, there's a lot of them that would be told to go and get scanned, right? In fact, sometimes they'll tell you, well, the CT scan is not working at Maina Soko, go to UTH, or UTH one is not working, go to Maina Soko. Because you have a lot of these things being generated on a daily basis, imagine how many of these things you'd have in a given month or in 3 months. In some instances, Lighton breaks his femur. You go to UTH, they get a scan, they'll put a cast, they'll tell me come back maybe after 6 months. What the radiologist or the referring physician would want to do is look at the image before and the new image. For them to get a hold of the image before, what we've done is we've built a system that they can search through, a PACS system. Now they're searching through millions of records, thousands of records, let's say that, right? Because we've automated the previously paper-based, it's a manual workflow, we'll call this. So they would search through the system, but what they're doing is they're searching using the DICOM metadata. Now, if you have DICOM metadata missing, you won't be able to easily find what you're looking for. So one of the obvious benefits of what we've done in terms of the work Elijah is doing is we've identified the weaknesses, the pain points. And in fact, he didn't mention the other scope of work which we are actually finalizing. We're building classifiers that are aimed at trying to see if we can automatically generate certain metadata, like the institution, for instance. Because the wider vision for this project is we are working towards setting up an archival platform which could potentially be used by a number of hospitals in Zambia. There are a lot of them, right? Which will do these scans. Chipata General Hospital, I don't know, Kanyama Level 1 Hospital, all right? And all these weird places. So we're saying we can build this platform which can be used as an archival platform. And the moment you're doing that, you have a lot more records which would have to be tagged in a certain way for people to find what they're looking for. Anyway, enough of the rant. I don't know if there are any other questions. Hopefully that helps answer some of the questions you had.
Well answered, Doc. Highly appreciated. Thank you.
All right. Are there any other thoughts or questions about this? We're expecting a lot of questions from the people who are enrolled in CSC 5741. Yes, Mr. Shikapande.
Yeah, my network is pretty bad, but the question that I have is, did you have some, can you guys hear me?
We can hear you.
All right, yeah. So the question that I had is, were there any unexpected findings that came up as you are doing the project? If so, how did you address them, Mr. Elijah?
All right. Okay, so during the analysis of the metadata, yes, so there were, I think, quite a number of findings that we had, so some things that we didn't expect. So just to mention one of them, this was the information that is normally entered by the radiographers. So most of the information that we actually found was that some information is actually entered wrongly or incorrectly. So others would actually put, maybe if it's the institution name, others would put the university teaching hospitals, while other files, after carrying out an analysis on them, others would have maybe UTH. Others would have UTH in capital letters, others would have UTH, the university teaching hospitals, in small letters. So there were quite a number of inconsistencies in the metadata as well. So for now, our main focus was only trying to identify if, to see whether they do enter the necessary information. And from there, we can actually work towards ensuring that the information is properly entered by the operators. I'm not sure if I've answered your question.
Yes.
All right.
Yeah, so
Any
again,
other
just to
questions?
add on to that, you know, the issue of like the solution, you didn't touch on how to address this issue, the problem. It's a serious problem, right? It's outside the scope of the project, and the project has a lifespan. We are hoping we can potentially extend this work at a later stage. But it's an issue of serious concern because again it compromises searching or browsing, you know, and also just to give you the sheer scope of all of this, right? You may think that this was an easy task. You know that a typical photo, right? The photo that you take using your phone or your digital camera will have anywhere between 15 to 20 metadata elements, right? Things like the file name, the type of camera that was used, the longitude and latitude, right? The GPS coordinates and all those things, the date, the timestamp. Well, DICOM files have, well, the current standard Elijah we're using is 5,000 and what?
The official one has got about 5,054,
Right.
but they are actually way more, about 5,300.
Yes, because they are private tags as well. You know, so the
Yes.
task was to see out of all of these 5,000 plus elements, what was the relative compliance? And really, if you look at the strategy that we employed, we are looking at creating weightings like Elijah mentioned, and then we get the final result by combining all the scores from the 5,300 metadata elements. They're called data elements anyway, if you read up the DICOM standard. In case people are interested in this obscure stuff here, we are extending a technique that we've employed elsewhere with different types of metadata. There's work actually that was done by a master's student. I don't know if Cecilia is attending this talk. She's graduating this month. So we're essentially applying that technique to DICOM files, because whether you are dealing with metadata associated with photos, with DICOM files, with ETDs, it's still metadata. Anyway, are there any other thoughts or questions? Okay, if not, we would like to take this opportunity. Elijah, maybe you can also share that public link here. I mean, it's a sandbox, and most of the images are anonymized, but people may want to poke around. And I was expecting, by the way, that some of the students enrolled in CSC 7.1 would say, can you share the data set that was used, right? These are questions we should be asking so that as we're working through the subsequent lectures, we can practice on those things. We may not use this data set as a case example, but just in case you want to look at these things here. But we want to thank Elijah for finding time off his busy schedule. If you can paste the link to the thing, Elijah, the PAX platform, that would be nice. We are really, really grateful, and also wanted to thank the people that, the audience that made it to the talk. Just to let you know that we have a few more talks scheduled between now and the first week of June. So we have a talk scheduled for next week. We haven't yet had confirmation, but either we shall invite a person who is working on a different aspect of this project, Malaysia, but his focus is on a work package that is centered around developing the AI mode I spoke about. The one that it's a detector and a classifier model. So it detects, it tells you, it's a binary classifier that tells you if a DICOM file is associated with pneumonia or not, right? What it also does is there's a separate detector model, a detection model that creates bounding boxes on the image to show you the problematic areas on a chest x-ray. Would really love it if you could attend, and who knows, maybe you will learn a thing or two just like we have in the last 2 years or so. So thank you so much, and thank you, Elijah. We hope to see you next week, same time. Good day. For the people enrolled in CSC 741, there's a separate link, I think, for class. We have class. Thank you, and bye-bye for now.
All right. Thank you very much.